appreciate it. Okay, so let's make a plan. Let's do my favorite thing and make a plan. Let's get rid of some of these. Yeah, this can go too. Cool. Let's make a plan. So, 1 VRAM. I feel like my my handwriting has not been quite the same since someone complimented me on it, and I got very self-conscious, or I got very aware that I was writing decently. So it's hard. So VRAM. Currently, our VRAM allocation strategy is if this is VRAM, right? We allocate something, we allocate something, we allocate something, we allocate something else, we allocate like a big thing, we try and allocate something else which would come out to like here, but we can't do it and we crash. We have an allocation strategy. It works very, very well. We do not have a deallocation strategy. There's no way to go back once we've taken up a bit of VRAM. Now, when I say allocate and deallocate, and let me just actually make a layer here so that I can erase things. When I say deallocate, what I really mean is we pick an address that we've used before, right? Because as far as our VRAM manager is concerned, and this is something I can actually implement entirely in Lua, right? When we allocate something in VRAM, we just imagine a number, right? We just get some number. It doesn't matter what that number is, as long as it's in the range 0 to 4 megabytes, right? 0 to 4 times 2 to the 9, or 4 times 10 to the. Okay, I need to actually work out if this is a 2 to the or a 10 to the megabyte or megabit. But megabyte or megabit, I don't know. But so we just pick a number in this range and that's cool. The hard part is making sure we don't like overlap things. So when we're doing this in practice, it's gonna kind of go like this. So the first thing we're gonna allocate is gonna be a frame buffer. The second thing we allocate is going to be a frame buffer. And these things are going to be pretty static, right? Once we've allocated a frame buffer, we never need to touch them, question mark. I'm not going to say never, but for now I'm going to assume we never touch our frame buffer. So really when it comes to textures and stuff, this is the point that we care about, right? This is kind of like a sub buffer. So if we say this is like X, right? If this is 0, this is 4 megabytes. Or megabits, need to work that out. We only care about this sub-region of VRAM. So I think if we build an abstraction, it should be an abstraction focused on sub-regions. Last stream I was talking a bit about, my kind of eventual VRAM strategy, which I think will be to divide this in half, have like an A buffer and a B buffer, and fill these up, I guess kind of, not independently, but treat them as two separate things. We fill up A and then we draw against A. And while we're doing that draw, we fill up B. And then once the draw on A is finished, we can draw against B and vice versa. We can kind of like flip-flop between two buffers several times mid-frame. The way the PlayStation 2 rendering works, we have very limited VRAM, but we have a lot of bandwidth between the motion engine CPU and the graphics synthesizer memory, VRAM. So what that means is we can send a lot of information during a frame, right? So maybe our abstraction actually has to be based around an idea of sub-ranges, or I guess slices of a buffer, right? VRAM is a fixed range, which can be represented by two numbers, 0 to the limit. We can take a sub-region of that from X to some limit, then we can take a sub-region of that. And this is really just like, if we want to like subdivide this, we just, we do, I guess we have to wonder if we're storing the start and the end or the start and the length. Probably the start and the length. I think you do a little bit more arithmetic in that case, but I think it's maybe, no. Okay, well that's like a question. That's like a question. Store as start end or start length. I mean, this is like a super, super unimportant question, but it's something we need to think about. It's something we need to think about. That's probably actually the only question we really need to tackle, right? Like I said, these are just numbers. So I think if it's maybe a little bit unclear even, it'll become very obvious once we start doing it how simple this really is going to be. And I'll show you the current VRAM allocation strategy as well, which again, is just doing math, like really basic math on numbers. So let's make a branch. VRAM manager, I guess, is an ambitious name, but better VRAM strategy. Okay. So if we load up VRAM.lua. Oh, my washing machine's beeping at me. That's a bit sooner than I thought. I'll ignore that for a little while. That'll be fine. So currently when we allocate in VRAM, right, we just have one magic number called base pointer. When we allocate, we try and add an aligned offset to that pointer, calculate if it overflows VRAM. Otherwise, we just give back, you know, our what's plus b here? Oh yeah, plus the number of bytes. Yeah. So the idea is that we have like a base pointer, right? Our output starts at the base. So our base pointer is our next allocation, right? We take where we start our next allocation, we make sure it aligns to some arbitrary, you know, alignment, like 64 bits, 128 bits. This algorithm actually is not, like, this algorithm works, but it's not the most efficient alignment. Sometimes, in fact, I think it is not the worst case alignment, but the worst case alignment within, if you're 256 byte aligned already, it will add a meaningless 256 byte gap, I think. There's some issue with this. I worked it out. I wrote it down somewhere, and then I forgot what the problem is. But this works. It won't crash the PlayStation 2, so that is good enough for now. We can always come up with a better alignment strategy later. And then we calculate the address we give back, and then we move the base pointer by the number of bytes we're allocating. And this is unaligned, so the next call then aligns to whatever alignment it needs. In practice, we could do our alignment here because everything probably will have the same alignment, but we're keeping this simple and letting the caller decide what to do about it. So the first thing we need to do, this max is good. Is it? Kilobyte, yeah. So we're saying this is 4 megabits. Okay. We'll go with this for now. I don't think this function gets used. Yeah. VRAM size is also a function I don't think gets used, right? I think instead we're using Draw2D, we're using like texture. Do I go VRAM? Yeah, I'm not calling it. VRAM alloc. So we actually probably should start using this. This is really useful, and this is probably a better way to think about allocating textures than our actual texture alloc function. Because yeah, like this is just doing a shitty version of this calculation, a primitive version of this calculation. It's actually weird. It looks like we're calculating this very differently. Okay, I'm getting distracted already. Am I disappearing in this light, by the way? I feel like my face is blending into the wall somehow. Anyway. What we actually need here is something more structured. So let's make VRAM So a VRAM buffer is going to have two pieces of information. It's going to have a start, and it's going to have an end, I guess. Oh, we can't call it end. We're going to have maybe... What's another word for end? Get me my thesaurus. Start to... Or maybe like head to tail. I don't love this, but it'll do. And so the default VRAM buffer is going to be all of VRAM. Let's say VRAM buff... So we're going to add some methods to this, and then we're going to use like a meta table to to share information, or to share this implementation, right? We're gonna go a little bit oop. We're not gonna go full oop. We're gonna go a little bit oop. That's my approach to this code base in general. So VRAM. Or I guess yeah. Let's have start. Let's have head, and then let's have tail. I think that works well. So let's go alloc the align. So this is going to be very, very similar to what we're already doing, but it's just going to reference self instead of using global variables, right? So out equals self dot head, out equals out plus align. That is still fine. Out plus bigger than max. Then this is fine. We need to change the logging there a little bit, and then instead of moving the base pointer, we move self dot head, and then we return out. Perfect. We'll get rid of this logging for now, and we need to say VRAM buffer overflow. How do we actually? I guess. I don't actually. There's a way to There's like a metatable way to give a table a string implementation, right? Because if we think about how we'd represent this as a string, we'd probably do it as just like a triple, right? We'd probably just say 0, 10, 100, right? And this would be the VRAM buffer that starts at 0, spans to 100, and has a head of 10. Or maybe like 0, 100, 10, or something. There are a few different ways you could serialize this that make sense. For now, let's just say VRAM buffer overflow. And then throw an arrow. Function VRAM buff. And now we also need a function that's going to let us subdivide these buffers. So when we take a slice, we want to do it. Do we want to do it from the current head? Or do we just want to imagine? Okay, so we've got two options. We can either think of this as a method of an existing VRAM buffer. So if we have a VRAM buffer that takes up all of memory, we would give it maybe X, and it would give us the remaining. Or do we just... What's the best way to explain this? So I'm imagining two situations, right? In one, we say the new buffer equals mem slice. Right, so we make a buffer from an existing buffer, or the other option is we say new buffer equals VRAM dot, or like does this make sense? So in one example, we're saying like take a slice from the current head of an existing buffer with a length, and in the other, we're just saying, hey, these are just numbers, just treat them as numbers. We're not doing anything fancy. I think this works a little bit better. I think this makes a little bit more sense, right? Rather than making it part of this like metatable definition. Rather than making it part of an existing buffer, right? A buffer doesn't really understand how to slice itself up. Or I guess there's no need for a buffer to understand how to slice itself up, because these are just numbers. It just feels like it would be baking like complexity and assumptions in. So this is a function of VRAM. So VRAM dot slice, start, end. No, we're calling it head. We're calling it tail, and we're returning return. It's going to be a table with head equals head, tail equals tail. Except it's going to be set meta table, and we're going to give it a meta table index equals VRAM buff. And I don't know why I've treated this like a function call. Perfect. This is kind of ugly formatting. I think we can do better. Yep. This is still kind of ugly. We'll wear that. We'll wear that. And there we go. That's it. This is our VRAM. This is how we manage VRAM smarter. Right? This is all it takes. VRAM size is actually also a really useful function. I'm really interested in why this is different to the texture calculation though. So I've obviously got some stuff to experiment with here. Our textures may be taking 4 times more VRAM than they need to. So that's not good. We shouldn't do that if we can avoid it. Oh, this is where I was using VPA. Okay. VPA here is actually just saying... it's actually just saying... We're going to copy this faulty algorithm up here. Size... Cool. And this actually makes more sense here because you always... No, this makes... There's a smarter way to align things. Again, this is mathematically sound. You can derive this from the idea that you want this thing to be equal to 0 modulo align. That's cool, but it's not the most effective way to do it. There are problems. Also, I wish Lua had bit shifting built in. That would save a few headaches. Yeah, for things like this where it's very like mechanical operations, like that would be cool. So we actually already have a VRAM buffer. Again, I don't think this gets used. I'm gonna delete it. I don't think there's any use for it. And then VRAM texture size. Again, I don't know how this is any different to VRAM size. So we're gonna get rid of it. We're gonna trim. This is a much cleaner, much more elegant take on VRAM management. So I guess the only thing missing now is the default buffer. So let's say VRAM dot, what do we call the default buffer? Do we just call it buffer? Do we call it mem? Do we call it m? Do we go really simple? VRAM dot buffer equals VRAM dot slice. I guess 0 max. So we have a default VRAM buffer, which is all of VRAM, and then we're going to take slices on top of that. So now if we come into, for example, our stress test, Wait, well, I was using this VRAM buffer function. This is so bizarre. Why was I doing this though? Because FB1, where does this get? Was this important to GS set buffers? Set buffers. Oh, it was important. Holy crap. So wait, what did I need? Okay, I need to unify my existing GS buffer and what I've just created with the like VRAM buffer. So VRAM. Let's take a few steps back. So this has an address, it has a width and a height, and it has a format. So we now have two competing concepts here. Okay, we have our existing so we have what we've called before VRAM buffer. This is used for allocations. What we're trying to define is this kind of VRAM buff. And this is used for region so they're kind of like opposites, right? Our existing buffer was something that a memory that had been allocated, right? A region in VRAM that we were passing to other things to reference, that was allocated and that wasn't going to change. We're now imagining a VRAM buffer as something that we allocate from. Literally the opposite thing. Oh, and I was using VRAM buffer. Okay. I see what's happening. So what we want to say instead here is VRAM alloc, right? Where we were VRAM buffering, we want a VRAM alloc. But we want to do something else with these addresses, I think. Do we? Okay, here's the question. In GSLua, do we do anything? We do. We get all of these fields. Pop, FB width, FB height, FB address, FB format. We use all these things. Okay, so we just need a frame buffer abstraction, right? Function, VRAM. Or do we put it in VRAM buff? Let's put it in VRAM buff. Let's go. Which has a width, which has a height, which has a PSM, and it has an alignment. Okay. We're basically copying what was here before. This is good. So yeah, so now instead of this confusing VRAM buffer name, well, I guess we're not really calling this VRAM buffer, though, are we? We're calling this VRAM slice. But we're treating it kind of like a buffer. So now instead of a buffer where we're explicitly calling this, we've moved this, we've called it frame buffer, which is actually what it is and what it's being used for. That's a good solution to a problem. That's a really good solution to a problem, I think. And then text to size can go. And then we need to do that other thing. VRAM dot... I guess let's call it VRAM.mem equals VRAM.slice 0 max. Perfect. So now if we go back to stress, okay, here we would say local fb1 equals VRAM.mem frame buffer. Right. Really small change, but I think actually has a lot of nuance that is important to us. Frame buffer 2, and then we also have a Z buffer. And these are all the same thing, right? These are all the same format. So nothing else changes here yet. Now I guess the next problem to tackle, right? So we've done good things here. We've done really good things. We've done everything we need to for this. So now we can come in, we can say local what do we call this? Let's say VR, right? Equals VRAM slice. So we make a new slice of memory. It starts at the current head of the entire VRAM buffer, and it's going to run to VRAM. Right, it's going to go to the end. I guess actually let's maybe make that the default behavior. I think that makes sense. So if when we call slice, if tail is nil, then tail equals max. If we don't pass in an endpoint, we just assume it's going to consume the rest of VRAM, right? Because this is going to be a fairly common thing. We allocate some things and then we subdivide. But also we need to export this max. So let's go VRAM.max equals max. Because if we wanted to make, say, an A buffer, so if we wanted to say like AB, we would have to go VRAM slice, VRAM.mem.head plus some offset with a length. And then this, yeah, so this would actually plus len, right? If we end up dividing our remaining VRAM in two, it'll look like this. And then we'll have to calculate the length as local len equals VRAM right? This would give us our 2 buffers. We would get, because these are just numbers, right? We calculate this length and then we just divide it by 2. Yeah, so we would actually have to do that division by 2. And then we'd also have to math floor it, so we just got a number. Right? But yeah, again, this is why I love this kind of abstraction where it's just a number, and the fact that the way we interact with this hardware is so pure that we can just take a number, right? We don't have to have anything more complicated than just dividing a number by 2 to have this logic of subdividing VRAM. That's beautiful, that's beautiful. But this isn't what we're gonna do for now. We're gonna keep this here just in case, I guess. But this isn't what we're doing for now. In fact, this code will actually not use our remaining VRAM slice. So this is perfect for now. If I go into main.lua, if I don't even need to build, right? I haven't started Docker for one thing. I don't know, another day, another instance of me questioning if I should just run Docker on startup. This is the eternal question, the eternal struggle. Cool. But I didn't even need to rebuild, right? This was an entirely scripted change. Ooh. Oh dear. Okay, something went bad. Attempted to call a nil value field alloc. Which alloc did I try and call here? Aha, yes. So this is actually now self.alloc, right? Where we're calling this within our VRAM. I should call this VRAM slice. Okay. Here, this is settling in. Let's settling in. VRAM buff, you are now VRAM slice. Now if I run, crashes again. Attempt to index number value local self. So if I go to line 15, doesn't this have an implicit? Oh, hold on. Yeah, because I'm not calling it as a method. Okay. Oh, there we go. Awesome. So that works. That's beautiful. Now let's do it for the texture example, but the texture example is going to start to call into focus another question, right? So let's go up here. Let's go up here. Question 2. Okay, ignore. Let me write a nicer Q so that it doesn't look as weird next to a number 2. I don't know why. A while ago I started writing my Qs like with the loop, so they look a little bit like number 2s sometimes. Okay, so question 2, right? Question 2 is, we have. So let's draw again. Let's draw again, right? So we go frame buffers, FB. Also has a Z buffer, right? So we've got this like lump of fairly static memory that's always going to be taken up every time. And then we have our slice start, right? So our like sub-region of VRAM. We're going to call this boy, let's call this boy alpha, right? Beautiful, beautiful Greek letter, alpha. How do we share right? At the moment, VRAM is like a global object, but alpha, you know, if we, for example, initialize alpha in our start function, how do we get this alpha anywhere else, right? We have this slice, it's a reference to a region of VRAM. How do we share that to code that needs to load textures? How do we socialize alpha, right? How do we make sure that people can get this when they need it? What does this data flow look like? So in this example, it's going to be really simple. We're abusing file scope here, so we're just gonna keep doing that. We're gonna say VRAM. It's gonna start at nil. We're gonna make these same changes here. So instead of buffer, we can say VRAM.mem frame buffer. Hold on, if I'm really smart about this, I can write a really good search and replace. Buffer goes to mem frame buffer. Yeah, perfect. That was a sick search and replace. Come on, you got to give me some credit for that one. So now we do what we were doing before, right? So we come in, we go, we say VR equals VRAM slice. We're going to start at vram.mem.head. Head? Wait, what did I call this? VRAM? Yeah, it has a start and a head. Yeah. But when I create this, I did it stupidly. Start equals head. There we go. So if I run this again, is it gonna... Yeah, it's gonna cry at me because I did something wrong. Is it? Oh, no, it isn't. No, it isn't. I just got impatient. That doesn't sound like me, right? Getting impatient? Cool. Okay. So we wanna focus in on this texturing example though, because the texturing example, you know, where we actually use VRAM after we initialize our buffers, that's gonna be where the meat of this starts to happen. So we make a slice from... We make this, right? We make this slice. And then now we can actually come and upload these textures. Oh, can we do this at the start? I actually don't know if we can. We need, I think we need the frame to have started to upload a texture now. So I guess one way to think about this, we could have like a dummy frame before we actually draw anything where we just clear the screen and upload textures. That would work. Need some kind of loading screen. That's interesting. Okay. So first off, we need to go into Draw2D and change how this alloc works. And I think we just don't want to allocate textures in Draw2D anymore. That doesn't make sense to be part of Draw2D, right? We're going to gut you. TT. Yeah. Cool. You're gone. You're out of here. This isn't doing anything fancy. You're done. Upload texture similarly probably shouldn't live here, but for now, because it has so much logic related to like fundamentally how we're building our draw buffers, this is gonna kind of have to live here. I guess eventually Draw2D and Draw3D will both share the concept of a draw buffer because they will have to live in harmony. So we'll have to abstract, I guess, some of this like buffer stuff out and this gift tag building logic. And they will both be, I guess, thin wrappers over a core draw buffer abstraction. But yeah, in conclusion, uploading a texture is actually fundamentally more related to drawing than allocating a texture is. So what we want to say here instead is, I think it's okay for VRAM to understand our texture struct, right? I don't have a problem with that. VRAM texture has a... Does it have a width and a height? Or does it just have a size? What did I actually just delete? Did that... Oh, that's right. Yeah, texture has all of this stuff built in. Like it already comes with these fields populated. Test text. Does it? See, the interesting thing about this is we're calling alloc. This like reads... I must have deleted something else here. That's okay. That's okay. Oh, it must be when we load, right? Did I just delete the part where we actually load these textures? Wait it. What? Oh, load texture. It's up here. It's up here. I'm going crazy. Okay. So we come back into VRAM. We allocate a texture from a texture struct. We do exactly this thing, right? So we go local size equals VRAM size. This isn't like related to the actual the actual properties of this slice, right? VRAM size is a global. So text, width, text, height, text, PSM, and then a line is going to be 256. We align all of our textures by 256 bytes. I don't know why. And then we say text.base address. Base address. Let's double check what field we're looking for. Base pointer. There we go. Equals self alloc. Size 256. Perfect. This will throw an error if it fails to allocate and ungracefully, right? Gracelessly tear down our entire program. Beautiful, beautiful. So we come back into texture, and now we say VR texture test text VR texture font, and I should be able to run this. Okay, so a few things have gone wrong. This flickering crap is caused by our texture being loaded. I think our texture. I actually don't know what's causing this. Hold on. I was going to say our texture's been loaded into our frame buffer, but that we would be seeing the opposite thing, right? If our texture was loaded into our frame buffer, when we cleared the screen, we would wipe out a chunk of our texture. What we're seeing instead is... But the order of these blocks makes it appear that this is actually like the VRAM representation of this stuff, right? So this... That's odd. Okay, so what's changed? What's changed? The main thing that's actually changed, I think, is calling VRAM size here instead of manually working out the size. So let's do that, right? Let's park this. Let's say local size equals text.width times text.height times 4. And this should hopefully work. Okay, it's a little bit different. It's a little bit different. This should not be any fundamentally different in any way to what we were doing before. This should not be different to what we were doing before. I'm definitely using head. Definitely using the head of the buffer. Let's just see if we're misusing the start of the buffer anywhere. Ooh. Well, that's probably going to do it, right? Where this is... So we were passing in an argument called start, but we were setting these things to an argument called head, which is nil. And if these things are nil, it's going to fall back to whatever was in the meta table. So in other words, yeah, I'm an idiot. I was drawing at the start of VRAM instead of where it actually should have been. But also simultaneously drawing in the correct position. It was like superposition, right? It's drawing in two places at once. Cool. Okay, so VRAM is now less stupid. The next thing that I really want to just quickly change is how these textures get uploaded. So once we upload a texture, we set a flag on that texture to say that it is currently resident in VRAM. So what I actually want to do is wrap this whole thing behind logic, right? If not res.resident, then if not test text. So if our test texture is not in VRAM, then upload it. And then if the upload's successful, it is resident in memory. Similarly, if not font.resident, then upload it, and. So this is going to mean that we only do this once rather than every single frame. Perfect. And this should save a lot of unnecessary thrashing. That's cool. That's cool. So, we only upload things once if we actually need them. That's good. I think I'm going to have to go and hang out my washing, so I'm going to take a quick be right back. It's just an inside line. It's not much washing. Should be pretty quick. I will be back shortly. And then we're going to start writing some C code to optimize this and make it better. Hopefully hit more than 1 FPS on our triangle test. All right, back in a minute. All right, boom, we're back. I think this is good. I think this is enough to work with for now. I really didn't solve this question, right? I didn't solve the question of how we share these references around, but this is just a normal, a normal data flow question. So what I'm gonna do? Oh, hold on. I'm not quite done. I need to clean up a few things in Draw2D, right? We're no longer using texture. I mean, load texture should not live here. This is pretty disgusting. VRAM alloc texture, you're gone. You no longer exist. Load texture needs to live somewhere else as well. Where do we put load texture? Maybe we need a new Lua file. Maybe we need texture.lua. I don't... Oh wait, no, that's the name of our test. Crap. We've got a name conflict. Okay, we'll leave this in Draw2D for now, but we'll put a to-do on it. It's pretty gross. It's pretty gross. Okay. This is great. This is phenomenal. So we're gonna make a new branch on top of this. We're gonna call it C Draw2D. So if we look into, oops, Draw2D, we're gonna port this from Lua into C, right? There's a bit of gnarly logic in here. It's going to take a little while. I'm only going to get this started today. I'm not going to do it all. I've got places to be and things to do. But yeah, we're gonna take a pass at this, right? Probably a good first candidate is going to just be our draw triangle function. We don't need loads of stuff for this. So like instead of calling this in Lua, we will call a C equivalent and it'll go a lot quicker. I'm excited about this. I'm excited about this. So let's go source draw. Let's call it draw2d.c, not draw3d. We're not quite there yet. And we're gonna make a function. It's gonna be called draw2d triangle. Gonna have a few arguments. It's gonna take three xy coordinates. So x1. So what do we got to do? I guess we actually can't just implement this one function, right? We're going to have to take everything because we need this state to be done in C as well. So there are going to be some static variables, right? Okay. So let's wrap it in a struct. Let's say struct. Let's call it our draw2d state. And we're going to have exactly one of these, which we'll call state. Cool. So a few things. We're going to have this color triple. That's going to be 4 bytes. We're going to have we're going to have what we're actively drawing, which we've called state here. We're going to call something else in C. We're going to have int loop count. Let's maybe split this up even more, actually. Let's maybe have struct let's wrap some of these things in nested structs. I think it's going to be neater. So struct d2d gif. Yeah, so d2d gif, this is going to be the stuff we need for drawing a gif tag. It's going to have a loop count. It's going to have, yeah, tag. Except we're gonna do these in the appropriate undercase thing. And we can simplify these names because we're going to have this like nested hierarchy namespace thing, right? Like because we've got structs within structs, we can actually be a little bit less descriptive with the names. The names will be implicit based on like the struct they're in. Loop count. Now the texture pointer needs to live outside of this. We'll call it a ref rather than a pointer, maybe. Oh no, we'll call it a pointer. Pointer is a fine word. Pointer is a fine word. Scares some people, but we're not afraid of pointers. Yeah, so we're gonna have a draw buffer. We're gonna have this. So let's say struct. We're gonna have the number of kicks. We're gonna have the number of tries that we've drawn. And then we're going to have two structs of this. So we're going to have a struct. And then we're going to have a struct D2D stats last frame. So we're gonna track stats for the you know, as we draw a triangle, we add it into this frame, and when we query, we're gonna query based on the previous frame. And we'll have a, oh yeah, maybe our Lua interface for this will need to change. So at the moment, if we look at, for example, stress.lua, we just grab the kick count directly like this. We might need to actually wrap this in a function just so it's a little bit easier to implement. There will still be a Lua wrapper into this, right? Like that'll still be required. Okay. And then we also need, like, so we have the stats for drawing a GIF tag. We also need the equivalent for, so struct D2D DMA, the equivalent for a DMA tag. So this is going to be, actually no, I don't think we need the quad word count, right? We'll say head, hold on, draw2D, not wrong, draw2D, draw2D.lua. Quad word pointer, in other words, the point to the head, and we're also going to have int is CNT, or in CNT. Perfect. So this is our state. This is everything that represents what we need to draw. So if we were to draw a triangle, let's do a side by side. I like this. Cool, so let's just like port this logic directly for now. So if state.gif.loop count is greater than 10,000, I don't know why I've chosen this magic number, but gif max loops, make that a little bit better, kick, draw2D kick. If okay, so we're also going to need, like, we're not going to have as nice of a buffer abstraction, right? Like, we're just going to have a list of things, or like an array, a dumb C array. So we are going to need int draw buffer length, and we're going to need int draw buffer head. So if state.draw buffer len minus state.draw buffer head less than 80, then we also need to draw2D kick. Cool. How many lines is this? How many columns? Sorry. So this is only 58 columns. We really, because I've got big terminal on, this takes up a lot of space. Okay. Also, my big fat head's going to be in the way. We'll try and minimize that where we can. So if state.drawType, so if we're not currently drawing geometry, in other words, triangles, then we need to make a GIF tag to set this up. So if self.drawType So literally just porting this logic beat for beat right now. And there's a lot of functions that are going to be missing. We're going to start with something complete, and then we're going to fill in the gaps. We're going to start with Swiss cheese, and then we're going to plug the holes with Gouda. So we need to make a GIF tag. maybe we just say gift tag new, I guess. We pass in our state, right? We pass in our state. Wait, this is... Yeah, we pass in a reference to our state. Let's offload this work where we can. Or like, I guess, you know, decentralize this work where we can, right? So we give it... Oh, no, we can't use this same abstraction though, right? We can't, unfortunately, can't use the same abstraction because this style of building registers just is not going to work in C. So we're going to have to define some magic constant. So gif reg... We're going to have a few magic constants for different register formats. And we'll see this as we go through. So let's say gif tag... gif tag... Yeah, let's just assume. Let's assume we've got all these functions. We may... I don't know if we'll have like a different function for everything like we do in Lua here. Maybe we will. Maybe we'll actually make these like inline functions as well. That might be kind of fun. That might be a fun optimization to explore. You know, increasing code size at the cost of less repetition for things we do. Or less, you know, function calls for things we do all the time. So, yeah, so this one... We know we only have one draw loop here, but then we need to make a tag that has, well, we need to actually like store a reference. So let's say gif, I guess we do this anyway though. State 0, 1, full 0. And then, so again, we kind of did this in Lua anyway. So we're going to say gif reg tries. So this is going to be a pre-calculated register format for what we're sending to the graphic synthesizer. And then we say, well, when we call gift tag new, that'll automatically do this. We're going to shoulder this in gift tag new. But then we do have to say that state.draw type equals draw2D geom. Perfect. So if we're not drawing geometry, if we were drawing something else, update the, like clean up the gift tag, then initialize gift tags for drawing geometry. Then we're going to come down, and then all we do, right? All we do is push the actual data for a triangle. So, gift tag packed RGBAQ. Or maybe we just say like push RGBAQ. Sure. Also, this isn't clear color. This is just color. RGBAQ. So we say state. Or do we wrap these three fields up into a shared buffer type that we pass in here instead of like everything? Ooh. Let's go simple. Let's go simple for now, right? We've got a few different types in here. They do important things. So state self state dot cull 0, state dot cull 1, state dot cull 2, state dot cull 3. So we pass in the colors, we remember our semicolons because we are good boys, and then we send in 3 XYZ coordinates because it's a triangle. Push XYZ 2. Yeah, and so then we also need this like macro. So we'll call it 2 coordinates still, I guess. X1 minus 320. Because we want the center of the screen to be, or we want the top left corner of the screen to be, wait, do we want the center of the screen to be 0, 0? Yeah, I think that's what we're doing here. And we always have Z set to 0. And so this is a little bit janky, right? Like we're hard coding a screen resolution in. It's fine. It's fine. Just roll with it. So here we replace x1 with x2, we replace y1 with y2, and here we do the same thing but with 3. Perfect. I think this works. We have one indexed argument names. That's okay. Oh yeah, and then we have to increase our loop count. So we say state.gif.loop count plus equals 1, and then we say state.stat this frame. Is that what I called it? Dot tries plus equals 1. What did I call it? Tries this frame last time. Yep, perfect, perfect. So this won't compile, right? This won't compile. This hits some issues. There are lots of things missing here. So first off, let's define some of these constants. Define gif max loops. After 10,000 loops, we say that is enough. Kick this freaking packet. Get this packet out of here. So we need to implement kick. Okay, let's oh dear, this is too many columns. Draw2D kick. Okay, what else do we need? I mean, we can actually get rid of this for a moment. What else do we need? What else do we need? Draw2D kick. We need... Oh, well, we can actually define this constant right now. Draw2D geom, Draw2D none. Let's start with none. Are these semicolons or are these... God, I can never remember the syntax for enums in C. C enum. That's it. I use them so rarely. Yeah, it is commas. It is commas. Perfect. And I mean, yeah, you can just use these as integers, so that's cool. And this is going to be draw type. A bit confusing because we've called the field that as well. That's okay. That's okay. It's a bit of gross name overloading, but it's okay. Some of this stuff will have to move into a header at some point, I think. But also, these things are only ever going to be used, except for stats. Stats is shared. These things are only ever going to be used internally. Okay. So kick, we need to implement Draw2D update last tag loops. We need to implement gif tag everything, and we need to implement push everything. Cool. And then once we've done that, we also need our frame start frame end. This should be enough to get us into a working example for our triangle stress test, I believe. Texturing, I think we'll need a few more things, like uploading textures, which will be gross. It'll be a lot cleaner in C than in Lua, but it'll still be gross. But let's see how much of a dent we can make in this for now. So draw kick, okay? Draw kick. So, oops. So the basic idea here is that we're filling up a buffer, right? Buffer, 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 with draw commands. When our buffer reaches the end, we call some magic kick function, which sends it off to the graphic synthesizer and resets our draw state. This one's really, really easy. Update tag last loops, okay? So while we're drawing, right? While we're drawing, sometimes we're gonna need to change the thing that we're drawing. So if we have, for example, let's say we're drawing triangles, and then we want to start drawing sprites. Well, we need to then tell this packet up here how many tries, right? So this is triangle, and this is sprite. And we only know how many triangles once we start this next packet, right? It's completely dependent here. So, so when we call update last tag loops, we just need to set one field in the previous gif tag, or I guess the gif tag that was previously being drawn. That's easy. The actual gif tag functions are just bit manipulation. So are the push functions, and then frame start and frame end will do a bit of manipulation. So this is probably the most complicated part, right? Like just keeping track of the state and making sure that we don't blow things up. So let's do this first. So in Draw2D update last tag loops. If you're wondering why I have a return signature on all of these, eventually I will return either success or failure. You know, as like a code, you can check the return type to see if your function was successful. For now, we're not going to do that. I'm just leaving the door open for later. So update last loops. Okay. So what we're going to have, let me put a marker here because we're going to be jumping back here quite a lot. So the head of our gift tag is a pointer into our draw buffer. So let's go, what do we treat this as? Is this a byte or is this a, let's grab it as a uint32t. Gift tag, we grab it from state.drawBuffer state.gif.head. Okay, so yeah, it's a pointer into our draw buffer. Maybe we should actually just store this as a pointer, then we can dereference it straight away. And actually, yeah, this is something we can simplify. So in Lua, we have to store this as a number because Lua, you know, we can't just have an arbitrary C pointer, or I guess we can, but it's messier. Here, let's just go uint32t head. Perfect. So we say, let me just double check I know what I'm doing. So yeah, the number of loops in a gift tag, right? A gift tag has a bunch of data in it, right? Blah, blah, blah. The data we care about right now, the number of loops filled, noop, and loop. Cool. This goes from bit 0 to bit 14. So we just set it, right? As long as it's a number less than 0x7ff, right? Is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 0, 1, 2. What I'm doing here is counting bits, right? So I think this corresponds to a mask 0x7ff. Okay, because if we expand this into binary, we get 0, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So if we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is our number of loops. So as long as our number of loops is less than this magic number, which is going to be 0x7 FFF. 32,767. So actually, when we come in to this max loops, we can define this better. We can say 0x7FFF, right? This is the maximum number of loops. Let's actually just like go down by 1, just to give ourselves a little margin. Refraction PCSX2 asks how I'm going. I'm going well. I showed earlier in the stream a bit of hardware gore where I pulled apart a PlayStation 2 this week and found a mod chip inside that I didn't expect. I bought a secondhand PlayStation 2. It was modded. That meant that it wasn't working with FreeMcBoot. Disaster struck. I almost bricked it, but I saved it. But the cable, the clasp that holds the cable that attaches the controller and Magic Gate module on, snapped. So that cable no longer sits in the clasp well, and I don't really know how to fix it. But it was fun. Even if it's bricked, right? I've now got like a spare parts PS2. I could actually pull the motherboard out. I think that might be a fun like teaching tool, right? When I'm programming things, I could be like, hey, here's a motherboard. Here are the bits on the motherboard that we're actually interacting with right now. I think that might be fun. But I'm pretty sure it's salvageable. Cool. So, update last tag loops. We need to make sure that the number of loops is correct. So if state.gif loop count. I think I called it loop count, right? Loop count. For some reason I lost my mark. Loop count less than gif. As long as it's less than that, we just set. So state.gif gif.head, so we dereference that. Oh, hold on. Wait, I need to think about this because there is an important flag, right? So the bottom 32 bits of a GIF tag, on the whole, there's not a lot we care about here, right? There are two fields in the first 32 bits, right? So there's the number of loops, and there's this I need a smaller EOP. That's not going to show up on stream, but that's fine. EOP, right? And then the next field starts at bit 46. So if we treat this as a 32-bit word, or a 32-bit, 32-bit word, we only have to worry about this extra field. So if we're just directly assigning to this, we have to make sure that we preserve whatever is in this EOP field. So the first thing we need to do, right? The first thing we need to do, let's go, let's grab the tag, okay? Now we want to say, let's say, we grab this. Let's grab the current state of this field. So if this is our mask for the number of loops, then the bit above it, all we do is take it and like just with this one top bit set, right? Bit 15. So then all we want to do is say state.gif.head equals state.gif.loop count or EOP. So we set the number of loops, and if this bit's set, we set it. Otherwise we don't. Yeah, so this is going to be this number if EOP is set, and 0 if it isn't. So if it's this number, we OR it together, we preserve the state of EOP. If it's 0, we OR a number with 0, you just get the number. EOP is not set. Perfect. And then otherwise, we're just going to have some like generic error function that says too many loops in GIF tag. We'll leave it at that for now. And then we return whatever success is. Let's return 1. We'll do the same here. Return 1. Perfect. Okay, so that looks a lot more elegant than it did in Lua, which is no shock, right? This kind of bit manipulation in Lua is not well suited to. Now we have this next function, Draw2D kick. This is going to be pretty simple. All we're going to have to do is call into the DMA side of things, right? So if we just like jump over Draw2D.Lua, kick. Did I go past it? Kick. So the first thing we do in a kick is call what we've already implemented, Draw2D update last. Probably want to check loops less than, FFF, because I'm doing this, I'm using this number for two things. I'm also using it to check here. I guess I can just change this to an equal, right? Greater than, or if it's greater than. Yeah, okay, yeah. I thought I would give myself a 1-bit margin just to make sure nothing, like, because I'm using this in two places. But no, you're right. I should actually just bite that. And I actually have like a safety check here. Even if this does get too big, it's just gonna it's gonna crash in a way that I expect rather than crashing in a way I don't expect. So as long as I have this error here and I check, we're gonna be fine. But one of these needs to be equal, right? Otherwise it's gonna, if this is greater than this, if it's less than this, this can be less than or equal to. But if the loop count's bigger than this, it's already too late. We're going to hit this error. Minus 1. Does that make sense? Yeah, sure. Let's roll with that. Sure. There's a lot of different ways I could cut this, but that will not crash, hopefully, as long as nothing goes wrong. It won't crash as long as nothing goes wrong. That's my favorite thing to say. Okay, so we update the last tag loop. We ignore end CNT. I guess let's put it in Draw2D end CNT, but we'll just kind of treat this as a no-op for now. In Draw2D end CNT, return 1. It just does nothing. We'll get back to DMA in a moment. Draw2D DMA end. Same thing. Int Draw2D DMA end. And then, yeah, so DMA send chain. I think it's like this. State draw buffer. DMA channel GIF, something like that. Channel pointer. Yeah, cool. But yeah, channel is just some magic constant as well. So the channel is like DMA channel GIF. I think that's how you do it. Cool. The pointer is going to be a state draw buffer. The number of chord words is going to be, yeah, the state draw buffer head divided by 16. So in other words, the number of chord words here. And then these fields are just always 0. It's easy. It's too easy. So we send the thing via DMA, and then we make a new buffer. I mean, and I guess this is actually just as simple as saying state.drawBuffer head equals 0 equals state.drawBuffer. Again, when we were in Lua World, we had to use like references into this. Now we can actually just go pointers direct. Cool. So we reset the head. And that's it. That's all we have to do. Get new memory. At the moment, we're reusing the same draw buffer, and this might have problems if we kick off a DMA transfer and then start overwriting things in the buffer while the DMA transfer like is still reading that memory. We may accidentally break things, but that's okay. We're just going to roll with that for now. And then we say state.thisFrame. We increment the number of kicks we performed in this frame. But yeah, this is going to be important as we go on. This is going to get increasingly important as we go on. So that's good. That's good, right? So we've got kick. Now we just need our functions to set up our GIF tags. And these are going to live potentially in a different file. I think that's important. I think they should live in a different file. GIF.c. And so these are just going to be a bunch of like really dumb small utilities. So like, let's go int GIF tag new. Draw state. We want to take in. What were these? What were these numbers? What do these numbers mean? GIF.lua tag flag number of loops and a packet registers. Cool. And then this has to be a very special, I think this has to be a uint64t, right? I think it's 64 bits. Yeah, the top 64 bits. So we really care about the integer format of this. We don't actually care about the formats of these other things. So we make a new GIF tag. we don't get to do our fun register processing, right? We don't get to pass this in just as a list. That's not going to work in C. We have to pre-compute it. So that makes our assembly a lot easier. So let's go. What's 32 plus 46? Let's get a low word. So this is state draw buffer, but as a uint64 t. And then we're gonna get the next two. I guess these aren't words, these are double words. Let's say LD and UD. S.draw buffer plus 1. Right, so two sequential 64-bit words in memory. This is going to be the content of our gift tag, right? So LD equals n loop. So let's go for something really fun. Again, so we're setting the bottom 15 bits here, right? So we need to check as well if n loop is greater than 0x7fff. Is greater than. Cool. If EOP it's not equal. So let's not even check EOP. But EOP is going to be 0 or 1. So if it's 0, we multiply this by 0, 0, or n loop is just n loop. If it's 1, then we get this or n loop. I don't know. I think this saves us an if. It might be nicer. Multiplication. I think this will get compiled down to something very, very smart. I think the compiler may be smart enough to work this out. Maybe I would need to flag that this is... I actually think regardless of if this is 1 or 0, even if this is like any combination of numbers, I think the compiler is smart enough to compile this down to something good. Then we need to set. So we don't set the pre-field. We don't set the prim field. We set the flag field. The flag is 2 bits at 58. So the next thing we care about, right? 58 to 59. So bits 58 and 59. Then we set nreg, the number of registers. That's 4 bits from... Well, I guess let's go. So from 60 to... So 58, 59 is going to be a flag. 60, 61, 62, 63 is going to be n reg. And then we're going to have the actual registers. All the way up to 128. I swapped sides here. That's a little bit confusing, but it's fine. It's fine. So, 58. So all we do here is say LD or equals... Oh, can we do this? Can we... Can we or equals a dereference like this? Maybe. We'll find out. The compiler might yell at us. The value of LD or equals flag left shift 58. Flag and 0x3. Because we only want a 2-bit number. Left shift 58. And this won't maybe I need to tell this it's a... there are cases where this can overflow. It's overflow 64-bit integer. It's fine. It's fine. I'm actually not concerned about this. Okay, and then the number of registers. Again, this is where I think it gets a little bit more scary. The number of registers. So this is a 4-bit number, so for one thing, we need to actually pass in the number of registers. Four-bit number, left shift by 60 bits. Cool. And then the upper double equals the actual register's value. This is kind of messy. This is kind of gross. It's fine. We'll survive. Int gift tag AD prim. Oh, and then we need to move the head, right? We need to move s draw buffer head. Oh, I did something weird here. Hold on. Where's my end of frame logic? The number, yeah, hold on. We want to say draw buffer head. The length here is draw buffer head minus state.draw buffer. Right, this is the number of bytes. So maybe actually let's calculate this up here. Int, I guess size t, buffer size equals state.draw buffer head minus state.draw buffer. Beautiful. This is good. And so let's see. Gift tag AD prim. So we have the state, we have the type of the primitive, and then we have 3 flags. Eventually we're going to need more than 3 flags, but that'll be good. AD prim. Prim AD, yeah. I'm gonna name things slightly differently here. Int shaded, int textured, int AA. Right, what flags do we have set in this primitive, in this primitive register? Okay, so when we set a register for use in AD mode, right? So set AD. Where's this defined? We use this a lot. Here. So yeah, so we push. So we have a 64-bit value, and then we have a register which is 32 bits or less. This is fine. So I'm trying to think of the nicest way to do this, right? We're going to be using this a lot. We're going to be calling this function a lot. We need something good. We need something meaty. We need something substantial, okay? So, gift tag. We're making a gift tag. We're making a loop in a gift tag, right? An entry in a gift tag for setting that a register via the AD register. I've talked about this stuff in the past. I won't go over all the details again, right? What we're doing looks like this. So we have 128 bits. 128, 0, 64. Okay, so we have the register that we're setting, and then we have the value. Almost every value is going to decompose nicely into two 32-bit values. That was important when we were working in Lua because we could only push one integer at a time, but now we can actually work directly in 64-bit land. It's just going to be a bit nicer in C. There was no reason we couldn't do that here, but Lua has weird behaviors when you get to very high numbers. They roll over into being floating point at a certain point, I believe. You lose integerness at a certain point. And because this is bit manipulation, the integerness is very, very important. So let's go. Let's say uint 64t. Let's do the same thing. Let's go lower double, upper double. We're gonna see this a little bit. Okay, we're gonna see this a little bit. Let's assume that we're gonna do this every time, and we're not. We're gonna have an abstraction for this in here somewhere, but let's assume we have to do it every time. So we have the doubles, right? The double words. We say the upper double equals gs reg prim. We say the lower double equals, okay, now here we go, 80 prim. 80 prim. AD prim AD. So we say prim, or I guess type is a better name for this. The primitive type, right? But the register's called prim. We'll not call the primitive type prim because we're setting the prim register, and that is too much prim for one man to handle. So it's this, or shaded times 0x8, or textured times 0x10, or AA times 0x80. So just like before, these are going to be 1 or 0. We multiply them by the corresponding bit mask, and then we OR everything together. And then we oh, we didn't even do this here. Plus equals plus equals 2 times size of uint64t. Right, we move forward by 2 unsigned 64-bit ints. And here similarly, draw buffer head plus equals size of 2 times size of. Let's define a constant for this, because we're gonna do it a lot, right? We're gonna use this a lot. Awesome. So pushing in a quad word. Similarly, we're gonna see. Well, these are the only 2 GIF tag functions we need. Then the other thing we need is this, like, push XYZ, push RGB AQ. And yeah, similarly, struct draw state S char R char G char B. And again, I think we can simplify this, right? We can just, well, I mean, actually, this stuff lives in the draw state anyway. Let's pass it in as an array of characters, right? And a bounds checked array of characters. We know that it's always going to be for long. The compiler should hopefully complain if we abuse this. So RGBAQ. How do we do RGBAQ? We just push these 4 integers. That's simple. That's simple. So let's go. How do we do this? How do we do this? And we could do it with a loop, right? We could say for we say uint 32t and then we dereference it and set it to culs I. Right, these are the same things. These things are equivalent, I think. The longer I look at this, the more I'm actually starting to doubt this ordering is correct. I don't know if this bracket is applied before the cast. I think the cast has higher precedence. So this should mean, in my head, this should mean that we cast. Oh, hold on, no, maybe not. Crap. What order does this stuff happen in? I want draw buffer head as a uint32t pointer to have I added to it and then dereference that. So maybe I need to do this a little bit differently, right? Maybe I actually need just another pair of brackets in here. That should do it, right? Maybe I need to do this here as well. And then we say s draw buffer head plus equals keyword size. Awesome. Oh, you can't see. Holy crap. Yeah, that's my big fat head is in the way. Oops. I should actually swap these around. I actually think I'm going to call it there. I feel like I'm running out of steam. But this is exciting. And once this works, we are going to get such a huge performance boost. It's going to be great, right? I'll probably like manually unroll these loops. I think the compiler should be able to unroll this, right? Like I should just be able to express what I want to express and let the compiler do it. We're using modern GCC. It should be fine. But this stuff, I don't know, maybe it looks gross, but the way I had to do this in Lua was just so disgusting. So I'm happy with this. I'm happy with this. I'm re-implementing some of what PS2SDK already has, but I'm doing it in my way with my draw buffer abstraction, my abstraction that lets me manage what is going on in the frame. And this is really exciting, right? I won't have to do a lot of thinking about what's going into GIF tags, right? This function does all the magic, okay? Where is it? update last tag loops, right? This means that I don't have to calculate things ahead of time. I can be very loosey-goosey with how I build gift tags. It's cool. I imagine that real PlayStation 2 games pretty much universally do this, right? Otherwise, it's just stupid. Or you have to, yeah, I don't know. There's all kinds of like stupid things. So, thank you very much for tuning in. This has been a really fun stream, a little bit longer than usual. Nice, relaxing way to start the weekend morning. Some good progress coming out. VRAM is looking fantastic. I might post a time-lapse of me almost butchering a PlayStation 2 to my YouTube channel. That might be a bit of fun. Thank you very much, everyone, for tuning in, and I'll catch you next time.